Hello everyone. Today we're going to be taking a look at queues, which is another data structure that we cover in this class. And queue, in many ways, can be thought of as similar to a stack. If you'll remember, a stack is a last in, first out data structure, which means when we push a key on a stack, if we pop the stack, the key to be removed is the last key to be pushed. And that makes a stack a last in, first out data structure. A queue, on the other hand, is a first in, first out data structure, which means that the oldest key is the next to be dequeued when the dequeue method is called. And so stack can be built using an array or a node, as we was what we looked at in the deck of slides on stacks. And one way to implement a queue is also using an array. We can do the same with the stack. With a queue, we can also use nodes, just like we would do, or I should say, just like we did in what we looked at regarding stacks. So stacks and queues are very similar. You can think of a queue as a line of airplanes getting ready to take off. You know, the airplane that's been in line the longest is at the front, and so the next airplane to take off is the next airplane in the line of airplanes. And when an airplane joins the airplane joins the queue at the rear, which means that particular airplane has the longest to wait to take off. And queue supports really fundamentally two operations. An enqueue operation, which is analogous to the push operation that we looked at regarding stacks. And then there's also the dequeue operation, which functions very much in the same way as the pop method does for a stack. So the first method we look at here is enqueue. Enqueue has two parameters, q, which is our queue, and x, which is the key that we're enqueuing. And in this method, if we look at the pseudocode, you can see we're setting q dot tail equal to x. So q dot tail is a subscript of the next available spot to perform an enqueue operation. And so q dot tail is effectively an array subscript, and q is an array, presumably. And so an array is one way we can do this. And in the pseudocode, we're making the assumption that we're using an array. However, this pseudocode can also be used to make a node-based implementation, which is better in some ways than an array-based implementation. You know, when you're implementing a queue, you basically have a choice between an array-based implementation or a node-based implementation. And in the pseudocode that we're looking at here, we're making the assumption that the underlying data structure is an array. So we set q dot tail equal to x, and if q dot tail is equal to q dot length, we know we have to wrap around to the beginning of the array. So we set q dot tail equal to 1. Otherwise, we're simply advancing q dot tail as we do in the else here, q dot tail equal q dot tail plus 1. And in the dequeue method, which is depicted here, you can see dequeue has a single argument, which is q, which is presumably the queue. which is essentially the array that we're using as the basis for the queue. And you can see when we dequeue, we copy q sub q.head to x, and then we check if q.head is equal to q.length. If that's the case, then we wrap around. We set q.head equal to 1. We wrap around to the beginning of the array. And if q.head is not equal to q.length, we're in the else, and we're setting q.head equal to q.head plus 1. So we're essentially advancing q.head, and that essentially removes the key at the front of the queue. And then we're simply returning x, so we're returning a copy of q sub q.head, which we extracted at the beginning of this algorithm. And here's a simple queue visualization. You can see we start out with an array, and we have 12 spots, sub 1 through sub 12. And we're setting, q.head is equal to 7, which is sub 7 in this array called q, which holds the key of 15. And you can see q.tail is equal to 12, which means when we perform an NQ operation, which we do, we actually perform 3 NQ operations between step A and step B. We put 17 in sub 12, 3 in sub 1, and 5 in sub 2. And you can see q.tail has been updated to 3, and q.head is still equal to 7. And then we call a dequeue operation, and we remove 15. You can see 15 is now grayed out, and q.head advances to 8. So for our node-based queue, we're utilizing a node class, which is depicted here. You can see we have a couple attributes, an int called key, which is our key, and a node called next, which essentially can be utilized to set up a chain of nodes, which we use as the basis for the queue. And we have a node constructor, and we're initializing both key and next with this parameterized constructor. And the isEmpty method of the queue is pretty simple. We're just returning front is equal to null. So in the event front is equal to null, we're returning true. And if front is not equal to null, it's more than likely front refers to a node in the queue, in which case the expression would evaluate to false, and we would return false. So with this isEmpty method, we're essentially able to distinguish between a queue that is brand new and has no keys in it, and a queue that has some experience and has already received keys via the NQ operation. And here in this slide, we see the NQ operation, which has a single parameter k, which is an int. And right at the outset, we allocate memory for a new node because we have a new key. And we test isEmpty. If that's the case, we set front and rear equal to temp. This is a new first node in the queue. And if the queue is not empty, the queue has some experience, and we set rear.next equal to temp, and then we advance rear by setting rear equal to rear.next to establish a new rear. And then we're printing a diagnostic message at the end of the NQ operation, and this can make it useful when trying to track the behavior of calls to this method. We also have a dequeue method, which has no parameters, no arguments, and we're checking to see if the queue is empty because we want to prevent underflow, which is what would occur if we were to call dequeue and not check to see if the queue is empty. If the queue is empty, we return -1. And remember, the keys are natural numbers, not including 0, which are the positive integers 1, 2, 3, all the way up to the maximum value integer can assume. And if the queue is not empty when we call dequeue, we're extracting front.key into this local integer called k. We're advancing past the front key to the next node in the chain of nodes. So we've essentially dereferenced the front, and we've set front equal to the old front's next, which is essentially the key which comes after the node that contains the key at the front. And one other thing we're doing in dequeue is we're printing a diagnostic message, and we're also returning k. And one thing you'll notice when we look at the queue app is that we don't do anything with the value that's returned by dequeue, and that's perfectly acceptable. And here's our queue app. You can see we're enqueuing 88, 77, and 66. We're calling dequeue twice. And if we look at the output, you can see we have our enqueues 88, 77, and 66, just as indicated before in queue app. And we're dequeuing, and 88, of course, is at the front, so 88 is the first to be removed. That's what makes the queue a first in, first out, or FIFO data structure. And we call dequeue again, and 77 is at the front after 88 is dequeued, so 77 is the next key to be dequeued.